Your lecturer is Stephen Ressler. Dr. Ressler is Professor Emeritus from the United States Military Academy at West Point, where he taught for 21 years. He holds MS and PhD degrees in civil engineering from Lehigh University and is a registered professional engineer in Virginia. Professor Ressler served in a variety of military engineering assignments in the United States, Europe, and Central Asia. He has focused his scholarly work and professional service in the area of engineering education and has won numerous national awards for engineering education and service.
Welcome to the wonderful world of do-it-yourself engineering, a unique 24-lecture learning experience in which we'll design, build, and test a variety of structures, machines, and devices, from a cardboard skyscraper to a concrete sailboat, from a radio-controlled blimp to a wooden mechanical clock, from a robotic arm to an electric-powered crane. The very title of this course, DIY Engineering, invites two questions. Why DIY and why engineering? But rather than simply answering these questions directly, I'd like to give you an opportunity to reflect on them while experiencing our very first DIY engineering project, and then we'll revisit them at the end of the lecture. So here's DIY project number 1. Our mission: to design, build, and test a mechanical device capable of launching a golf ball and hitting a target placed exactly 10 feet away. Now, for all projects in this course, we'll be using this approach, the engineering design process, consisting of 7 steps organized into 3 broad phases: design, build, and test. Every engineering design begins with a definition of the problem, addressing both design requirements and constraints. This project has 2 critical design requirements. First, the device must be capable of launching a standard-sized golf ball, which has a diameter of 1.6 inches and a weight of 0.1 pounds. And second, it must be capable of hitting an 8-inch diameter target placed 10 feet away and at the same elevation as the launcher. The project also is subject to 3 important constraints. Our project budget is $20. The device must be fabricated from commonly available off-the-shelf materials and parts, and due to fire safety restrictions here in the Great Courses studio, the device can't employ any form of combustion. Now, having defined the problem, we'll develop a range of alternative design concepts which have the potential to satisfy our requirements and constraints. Now, at this early stage in the process, design concepts are typically not defined in great detail. Rather, they're usually little more than sketches. Thus, for example, we might consider devices that propel the golf ball by means of a large rubber band, much like a slingshot mounted on a pivoting base, or a steel spring mounted within a cylindrical launch tube, or compressed air supplied by a bicycle pump, stored in a pressurized chamber, and released by a valve. Now, in comparing these alternatives, it's clear that the compressed air alternative would be much too expensive, and the rubber band alternative would be insufficiently accurate because of variability in the mechanical properties of rubber bands. The spring-powered concept is both simple and inexpensive, and because the mechanical behavior of a steel spring is highly predictable, it also provides the best potential for success. So let's select this concept and proceed with the detailed design, which can include such tasks as experimentation, modeling, analysis, and selection, though not always in that order. The most important task in our detailed design for the golf ball launcher is to select a steel spring with the right physical and mechanical properties to meet our performance requirements. To facilitate this choice, let's begin with some experimentation to increase our understanding of springs. Now, a spring is a device that stores energy through elastic deformation of a material. There are many different types, but the most common is the coil spring, which you encounter every day in common devices like this ballpoint pen. Coil springs come in two different flavors: tension springs, which are designed to be stretched or elongated, and compression springs, which are designed to be squashed or shortened. The only physical difference between the two is that the compression spring has some space between the coils, so there's room for shortening, while the tension spring has its coils packed tightly together to allow the largest possible tensile elongation. The mechanical behavior of both types is essentially identical. When I compress a compression spring, it pushes back with a resisting force. When I stretch a tension spring, it pulls back, again with a resisting force. And in both cases, the magnitude of the resisting force is directly proportional to the spring's change in length. Now, this is a very important characteristic, so let's verify it by investigating the relationship between force and length in springs experimentally, and plotting our data in real time on this graph. When we place 1 on the platform, you'll see that the spring elongates about 1/2 inch. When we add an additional 1.1 pounds, the spring's extension doubles to 1 inch. And with a third, it triples to 1.5 inches. The graph plots as a straight line, which verifies that the spring force is indeed directly proportional to its change in length. We can now use this graph to define the spring's most important mechanical property, its stiffness, defined as the amount of resisting force developed in the spring per unit change of length. Stiffness can be visualized as the slope of this graph. A spring with a steeper slope is stiffer because it develops more force for a given change in length, while a spring with a shallower slope is less stiff. Slope is calculated as rise over run. So for this particular spring, the stiffness, customarily represented by the letter K, is 3.3 pounds divided by 1.5 inches equals 2.2 pounds per inch. Thus, the manufacturer's product description for this spring would specify its stiffness, also sometimes called the spring rate, as 2.2 pounds per inch. Now that we understand the concept of stiffness, we're ready to tackle the next steps in the engineering design process: modeling and analysis, to determine the required stiffness of the spring we'll need for our golf ball launcher. Now, in this context, a model is a graphical representation of the essential components of our mechanical system, defined in a way that facilitates the application of scientific principles to predict the system's performance. And the most important scientific principle we'll be applying to analyze our golf ball launcher is the law of conservation of energy. Now, you've probably encountered the law of conservation of energy before, perhaps in a high school science class, perhaps in another Great Courses lecture series. If so, you might recall its definition, that the total energy of an isolated system must remain constant, or its implication that energy can neither be created nor destroyed, but can be converted from one form to another. But even if you're already familiar with this rather abstract principle, could you ever have imagined that the law of conservation of energy would serve as the vital tool for ensuring that a spring-powered golf ball launcher hits its target? I thought not. To set the stage for applying conservation of energy, we must first model our mechanical system. And here's our model, consisting of the projectile, a cylindrical tube that guides the projectile launch, the spring, and a sliding piston, which keeps the spring centered in the launch tube. To cock the launcher, we'll compress the spring by applying a force, F, through a distance, S. And then we'll lock the piston in position with a trigger. As the spring is compressed, it stores elastic energy. And the amount of stored energy turns out to be equal to the area under our force versus change in length graph, as shown here. This area is triangular, so it's easily calculated. The area of a triangle is 1/2 base times height, or in this case, 1/2 S times F max, the maximum cocking force. But we already know that the spring stiffness K is equal to the slope of this same graph. Slope is rise over run, or F max divided by S. So, using a bit of algebra to combine these two equations, we find that the energy stored in a spring is equal to 1/2 Ks squared. This is the total energy of the system just prior to initiating the projectile launch, a configuration we'll call state 1. Now, when we pull the trigger, the compressed spring rebounds back to its original length, and the piston and projectile are accelerated through the launch tube. Let's freeze the action right here, just before the golf ball leaves the launcher, and call it state 2. Okay, as the system moves from state 1 to state 2, energy must be conserved. That's the law. But at state 2, the spring is no longer compressed, so it no longer holds any stored energy. Therefore, at state 2, 100% of the elastic energy that was stored in the spring at state 1 has now been converted into other forms of energy, predominantly the kinetic energy of the moving projectile and piston. Kinetic energy is the energy associated with a mass in motion, and it's calculated as 1/2 times mass times velocity squared. Thus, the law of conservation of energy tells us that the spring energy at state 1 is approximately equal to the kinetic energy at state 2. Or, more specifically, 1/2 Ks squared is approximately equal to 1/2 times the total mass of the golf ball and piston times the launch velocity squared. Now, I've emphasized the approximate nature of this formulation because there are some other energy transformations occurring during this movement from state 1 to state 2. For example, some energy is lost to friction as the projectile and piston slide along the tube. But these effects are relatively small, and so for the sake of simplicity, we can ignore them, at least for now. Well, we now have an equation representing the conservation of energy in our mechanical system. But can we solve it? Well, we know the mass of a golf ball, we can estimate the mass of the piston, and to some extent we can control the spring's change in length through our design. But there are still two unknowns in this equation: spring stiffness and launch velocity. So we can't solve it yet. Wouldn't it be nice if we could figure out the launch velocity required to fling a golf ball 10 feet? Then we could solve this equation for the stiffness, K, and then we'd have a powerful basis for selecting just the right spring for the job. Well, in fact, we can determine the required launch velocity using this projectile motion equation, which is derived from the basic equations of motion covered in every high school physics course. The equation defines the range of a projectile as a function of its launch velocity and launch angle, assuming the air resistance is negligible. By the way, if you've never taken a course in trigonometry, don't panic at the sine and cosine in this equation. For the purpose of this project, all you really need to be able to do is plug the relevant numbers into the equation and obtain the answer with your calculator. Now, here's the same projectile motion equation plotted as a series of graphs of range versus launch angle for various launch velocities. Note that no matter what the velocity, the theoretical maximum range is always achieved at a launch angle of 45 degrees. On this basis, we might be tempted to design our device for a launch angle of 45 degrees. But this would be a mistake, because it would severely limit our ability to make range corrections by adjusting the launch angle. Here's why. Recall that in our analysis, we've made a number of simplifying assumptions, like neglecting friction and air resistance. Because of these simplifications, the actual range of our launcher will inevitably be somewhat less than the predicted range of 10 feet. If we design for a launch angle of, say, 30 degrees, and then the projectile falls a bit short on our first test, we'll be able to adjust the range upward by increasing the launch angle slightly. But if we designed for 45 degrees, this sort of range correction wouldn't be possible, because any adjustment of the launch angle above or below 45 degrees would only reduce the range. Given this decision, we can now substitute an angle of 30 degrees, a range of 10 feet, and the acceleration of gravity, 32.2 feet per second squared, into our projectile motion equation, and use algebra to solve for the required launch velocity, which works out to 19.3 feet per second. Well, this is quite exciting, because we can now return to our conservation of energy equation, substitute this number, 19.3 feet per second, for the velocity, and then solve for the required spring energy, about 0.7 foot-pounds. Oh, and by the way, foot-pounds is a valid set of units for energy, an observation that should give us some added confidence in this result. Okay, we're getting close. We now know that the spring energy, which is 1/2 ks squared, must be at least 0.7 foot-pounds to achieve the desired range of 10 feet. But before we can go shopping for a spring, we still need a specific value for the stiffness K. Now, as I noted earlier, we can control the shortening of the spring through the design of our launching mechanism. Thus, for now, I'm simply going to assume a value of 2 inches, which seems roughly consistent with the scale of our machine. Substituting s equals 2 inches into the equation, we can finally solve for the required stiffness K, and the result is 4.2 pounds per inch. Now, let's go shopping. One of my favorite online vendors for hardware, like metal, plastics, fasteners, and springs, is a company called McMaster-Carr, which we'll use extensively throughout this course. McMaster-Carr has a superb website with an excellent search engine, which I'll now use to search for compression springs. And here they are. Wow, there are hundreds of springs on this page, and several of them would work adequately for our design. But this one here is particularly well suited for our needs. It has an overall length of 3 inches and a compressed length of 0.74 inches, meaning that its maximum allowable change in length is 2.26 inches, which is more than adequate. It has an outside diameter of 0.48 inches, small enough to fit inside our launch tube, and most importantly, it has a rate, or stiffness, of 5.1 pounds per inch, just a bit higher than our requirement of 4.2 pounds per inch. This higher stiffness will work just fine as long as we compress the spring somewhat less than the 2 inches I had previously assumed. To determine the required spring compression, let's return to our conservation of energy equation once again, this time substituting the stiffness of our selected spring, 5.1 pounds per inch, and solving for S, which now works out to be 1.8 inches. Okay, having used conservation of energy as the basis for selecting our spring, we're now ready to fill in the remaining details of our design. For this purpose, I've used a 3D modeling software package called SketchUp, which is easy to learn, quite powerful, and free for non-commercial users. We'll be seeing a lot more of this wonderful DIY tool in future lectures. For now, let's use SketchUp to review my completed design for our golf ball launcher. Here's the launching mechanism. The piston and steel spring mounted inside a plastic tube. The tube is supported by a wooden stock, which incorporates the trigger, positioned to engage the piston at 1.8 inches of spring compression, and a protractor to measure the launch angle. The stock is attached to a wooden base with this bolt, which serves as a pivot, accommodating launch angles between 0 and 45 degrees. All of the wooden components for this project were made of poplar, my preferred wood for DIY projects. Poplar is stronger and harder than pine, so it's much more durable, and still it's easier to work than harder hardwoods like oak and maple. The spring and plastic tube for our design are both available from McMaster-Carr, and everything else can be found at your local building supply store for a total cost of about $10. The design phase of our process concludes with the development of drawings and specifications, which are used to communicate the design to others. You'll find these documents, detailed drawings, a materials list, step-by-step assembly instructions, and a set of full-size cutting patterns in PDF format in your course guide, along with the address of our DIY Engineering Resource website, where you can download my SketchUp model. And now, with the design phase of our project complete, we can head to the workshop and build this thing. This is the DIY Engineering Makerspace, where we'll be implementing the build phase of all our course projects. In setting up this workspace, I've opted for a limited number of relatively inexpensive benchtop power tools, which would be suitable for a modest home workshop in a basement or garage. We'll familiarize with these tools momentarily. Our shop setup also includes a large flat work surface, a benchtop vise, a vacuum cleaner for dust control, and an assortment of hand tools and clamps. Before we put these tools to work, a few words about our number one priority for all DIY activities: safety. When you're working in the shop, always wear eye protection, either conventional glasses or safety glasses, and avoid loose-fitting clothing that might get caught in a machine. When using noisy power tools, wear hearing protection. And most important, stay focused. In particular, be obsessively careful about keeping your hands a safe distance away from any moving blade. Ever cognizant of safety, we're now ready to fabricate and assemble the components of our golf ball launcher. First, we'll start with these elements of the stock and base, all of which are 3/4 of an inch thick and 3.5 inches wide. Now, these happen to be the actual dimensions of a nominal 1x4 board. So if you're using 1x4 lumber, you can skip this first step. But I'm using 1x6, so I'll need to trim the board down to a 3.5 inch width. This type of cut, parallel to the wood grain, is called a rip cut. And the preferred tool for rip cutting is the table saw. I'll prepare for the cut by positioning this fence exactly 3.5 inches from the inside of the blade, and adjusting the height of the blade such that it just barely protrudes above the top surface of the wood. Now, after donning eye and hearing protection, I'll start up the saw, set the board firmly against the fence, and feed it slowly but steadily into the blade, using this push stick to keep my hands clear of the blade for the final few inches of the cut. Next, this 3.5 inch wide board must be cut into several different lengths, which I'll measure and mark on the board. Such cross-grain cuts are best done with a miter saw like this one. First, by placing the workpiece against the fence, then lowering the blade, positioning the wood such that the mark is aligned with the blade's inside edge, and making the cut. The miter saw also works quite nicely for trimming the plastic launch tube to its required 5.5 inch length. For curved or unusually shaped pieces like this one, we'll use a paper cutting pattern, printed on plain paper and cut out with a razor blade or scissors, and then coated lightly with spray adhesive and adhered to the wood. The component can then be cut out with either a bandsaw or a scroll saw like this one. The scroll saw won't make a perfectly clean cut in thicker wood, so I generally cut just outside the line like this, and then use my power sander to achieve the final shape. For these 1/4 inch bolt holes, we'll use a drill press. When drilling wood, always put a piece of scrap material behind the workpiece to prevent the bit from splintering the backside of the hole when it breaks through. The great advantage of using a drill press rather than a hand drill is that it produces a hole that's perfectly perpendicular to the face of the workpiece. This component of the launcher requires a 2-inch diameter hole to accommodate the launching tube. To do this job, we'll use this hole saw mounted in the drill press. A hole saw applies very large torque or twisting force to the workpiece, so be careful to grip the piece firmly. Note that the hole saw incorporates a conventional 1/4 inch drill bit, which projects just ahead of the saw teeth, allowing us to center the hole accurately and then to use the resulting pilot hole to cut inward from the backside for a nice clean edge. Okay, having used these basic techniques to fabricate all of our project's required wooden components, we'll now remove the paper patterns using lacquer thinner to soften up the adhesive, sand each piece to remove any rough edges, and assemble the launcher using wood glue and clamping each joint until the glue has set. Then, to reinforce key structural joints, we'll drill pilot holes and add wood screws like this. The plastic launch tube is now inserted into the stock, and the stock is attached to the base with a 1/4 inch bolt, a washer, and a wing nut. The piston is composed of 4 components: an aluminum shaft, a wooden disc, and 2 retainer pins. The shaft is cut from a piece of aluminum tubing using a hacksaw and a file to smooth the cut, and then drilled to accommodate the trigger and the retainer pins, which are made from steel nails. We'll assemble the piston by mixing up a batch of epoxy glue, which is well suited for adhering metal to wood, and using it to secure the disc to the shaft and forward retainer pin, like this. After the glue has dried, this assembly is inserted through the spring and through the rear of the stock, and then secured with the rear retainer pin. The trigger is made from steel wire, bent into an L shape, and the launch angle indicator is a piece of string with a weight tied to its lower end. Our DIY golf ball launcher is now complete and ready for testing. First, I'll clamp it to the table exactly 10 feet from our target. Now I'll load the projectile and compress the spring. Set the trigger, set the launch angle to 30 degrees, double check my aim, and pull the trigger. Not bad. As expected, the first shot fell a little short, also a bit to the left. So I'll reload, increase the launch angle by a few degrees, adjust my aim, success! Well, now that you've seen DIY engineering in action, we can finally return to the 2 questions I posed at the very start of this lecture. Why DIY and why engineering? Why DIY indeed? In today's internet-enabled consumer economy, we can buy just about anything we want on a moment's notice. Why bother making a projectile launcher when we can find shelves full of them at the local toy store? I can buy this electric-powered radio-controlled model airplane for less than $25 online and have it airborne 15 minutes after its arrival on my doorstep. Why spend weeks designing, building, and flight testing this comparatively crude DIY version? Well, in my view, there are 2 compelling answers to these questions. First, doing it yourself is immensely satisfying, particularly when the thing you build actually performs some useful function. When the DIY airplane you've created from little more than an idea and a pile of balsa wood finally takes to the air, the sense of accomplishment is just incomparable. This sort of satisfaction simply can't be obtained from a factory-made product. And second, building something yourself always yields important insights that can't be attained through interactions with a commercial product. This toy airplane has been purposefully designed to be operated without actually knowing anything. But you can't possibly create this airplane without learning some fundamental principles of aerodynamics along the way. These ideas were beautifully articulated by John Ruskin, a 19th century art critic and philosopher who often railed against the inexorable trend toward mass-produced, machine-made goods replacing the handmade artifacts of an earlier era. In his book, The Seven Lamps of Architecture, Ruskin wrote, "All the short and cheap and easy ways of doing that whose difficulty is its honor will not make one of us happy or wiser. They will extend neither the pride of judgment nor the privilege of enjoyment. They will only make us shallower in our understandings, colder in our hearts, and feebler in our wits." Why DIY? In Ruskin's words, because it offers both the pride of judgment and the privilege of enjoyment. In short, because its difficulty is its honor. And lest you think that Ruskin's 19th century perspective is hopelessly outmoded in our modern high-tech world, witness the maker movement, a 21st century cultural phenomenon populated by increasing numbers of people from all walks of life who revel in the simple joys of building things. The movement is manifested in a growing number of maker spaces, community-based workshops in which people can create and learn in a social context, and maker fairs, public exhibitions at which makers proudly display their creations. The emerging maker culture provides dramatic and exciting evidence that the spirit of Ruskin is alive and thriving in the 21st century. And now, why engineering? Well, as you experienced in our recently completed project, engineering is a methodical process by which math, science, technology, and experience are applied to create a device or system that serves a purpose. Like engineering, DIY endeavors also involve the application of technology and experience to create useful things, but usually without a heavy reliance on math and science. There's nothing wrong with this, of course. As the maker movement demonstrates, simply building things is a wonderfully worthwhile endeavor in and of itself. Yet, I suggest that DIY, augmented by the rigorous application of math and science, takes making to a new level. To understand why, consider the golf ball launcher we just created. I'm sure you recognize that we could have implemented this project successfully without applying any math or science at all, simply by using trial and error. We could have obtained a large assortment of different springs of various sizes, and then tested each one in the launcher until we found one that achieved the desired performance. Yet this trial and error process would have been highly inefficient, because we'd have to buy and test many springs rather than just one. And it would ultimately have been less effective, because in choosing more or less at random from hundreds of available springs, it's highly unlikely that we would have selected the best one for the job. Even more importantly, if we had used trial and error for this project, we would have missed all sorts of opportunities for learning about conservation of energy, projectile motion, experimentation, algebra, graphical representation of data, and most important, the engineering approach to problem solving. Even if we had some appreciation for these concepts prior to this project, I'm betting that our understanding has deepened because we applied them in a practical, real-world context. This is what DIY engineering is all about, and this is why DIY projects, while integral to this course, are not its central focus. Rather, the projects serve primarily as the means to an end, the means by which we'll deepen our understanding of math, science, and technology in the real-world context of engineering problem solving. Next lecture, this problem-based learning experience continues as we embark upon a series of projects aimed at understanding the science of structure. Let's do it.